Hello students, welcome to your classical mechanics class. As in a previous lecture we have learned about the homogeneity of space and law of conservation of linear momentum. In the similar way, in this lecture we will learn about the isotropy of space and conservation of angular momentum. As the meaning of isotropy of space is the rotational invariance. That means we are considering a S frame of reference whose x-axis, y-axis and z-axis are like this and origin is O. Now let this frame of reference be S frame of reference. Now as we are talking about the rotational motion, so we consider another frame of reference. Let it be denoted by S prime frame of reference whose origin coincides with the S frame of reference, but the x-axis and y-axis rotates at a small angle d theta about z-axis. That means the z and z prime axis, that means the g-axis of S and S prime frame of reference coincides with each other, but there is angle d theta between x and x prime and y prime axis. Now in this system we consider we have two particles, particle 1 and particle 2, whose masses are m1 and m2 respectively. Now the position coordinate of particle 1 in S frame of reference is, let it be x1 y1. What is the meaning of this x1 y1 position coordinates? So if I draw a perpendicular from the position of particle to the x-axis, then this distance from the origin is x1 and this distance from the origin is y1. So this is position coordinate x1 y1. Similarly, the position coordinate of particle 2 in S frame of reference is x2 and y2. Now in S prime frame of reference, the position coordinate of particle 1 is x1 prime and y1 prime. So I will draw a perpendicular from position of particle 1 to the x-axis and the y-axis. So let it be x1 prime. So this is the position coordinate of the particle 1 in S prime frame of reference. Similarly, the position coordinate of particle 2 in S prime frame of reference is x2 prime and y2 prime. So let it be x2 prime and let it be y2 prime. So as the angle d theta is between x prime, y and y prime, so this angle will be d theta. Now we want a set of transformation equations so that we can see the relation between, we can find out the relation between primed quantities and unprimed quantities. Here the primed quantities are the position coordinate of particle 1 and 2 in S prime frame of reference, and the unprimed quantities are the position coordinates of particle 1 and 2 in unprimed frame of reference, that is S frame of reference respectively. So now we will start from the isotropy of space, but before going into the isotropy of space we will find out the set of transformation equation between the primed quantities and unprimed quantities. So we will start first for the x1 prime. So x1 prime is the position coordinate of the particle 1 in S prime frame of reference along the x-axis. So it can be obtained x1 prime equal to component of x1 along x-axis plus x prime axis plus component of y1 along x prime axis. So this will give us a relation between primed quantities and unprimed quantities. So component of x1 along x prime axis is x1, this angle is d theta. So this angle is d theta. So this portion of diagram is like this. this is x1 cos d theta, as this angle is d theta, and plus component of y1 along x prime axis. So this is y1 sine d theta. As we consider the z-axis coincides with the z-axis, that means frame S prime is rotating about the z-axis with a very small angle d theta. So d theta is infinitely small. So cos d theta is approximate equal to 1 and sin d theta is approximate equal to d theta. So we can write x1 plus y1 d theta. So this is x1 prime. Now we will find out y1 prime. y1 prime is component of, this is COMP's component of x1 along y prime axis plus component of y1 along y prime axis. So this will give us the relation between primed and unprimed quantities for their component along y axis. So it will be component of x1 along y prime axis, it is x1 cos 90 plus d theta, you can see in the diagram very clearly, plus component of y1 is along y prime axis, it will be y1 cos d theta. If you have any doubt, you can ask me. I will discuss in a separate video how this cos d theta, cos 90 plus d theta. Otherwise, you can clearly understood, or you can go through the Cartesian or spherical polar coordinate system, where we have already discussed how we find out the components along the x-axis and along the y-axis. Still, if you have any doubt, you can ask me in the comments. I will try to reply with some more clarifications on this. So x1 cos 90 plus d theta. So as we know, d theta is very small, so cos d theta is almost 1. So this term is y1. This term is minus x1 sin d theta. Since cos 90 plus d theta is minus sin d theta, so we can rewrite it as y1 minus x1 sin d theta is d theta. So it will be d theta. So we have the relation between x1 prime. So this x1 prime is x1 plus y1 d theta, and this y1 prime is y1 minus x1 d theta. Similarly, we can find out x2 prime is x2 plus y2 d theta. You can find out, or you can replace x1 with x2 and y1 with y2 in this relation, and similarly y2 prime is y2 minus x2 d theta. So finally we have four relations which gives the relation between four equations which gives the relation between primed quantities and unprimed quantities. So which is the component of the particle along the x-axis and y-axis in two different frames of reference which are rotating with respect to each other at a infinitely small angle d theta. Now as we know, now the potential energy of the system is a function of x1 by 1, x2 by 2. Since in this system we have two particles and their position vector are x1 by 1 and x2 by 2. So potential energy is function of all the four coordinates x1 by 1 and x2 y2 is equal to u prime x1 prime y1 prime x2 prime by 2 prime. So why I write the potential energy in this frame of reference is equal to potential energy in this frame of reference? This is from the property of space. So since the space is homogeneous, so the potential energy in the two frame of reference is same. So I write u x1 y1 and this. Now we will use this expression and substitute the values of x1 prime, y1 prime, x2 prime, y2 prime. So let us write here u x1 y1 x2 y2 is equal to u prime x1 prime by 1 prime x2 prime y2 prime. Okay. Now, as we know, x1 prime is, it will be u prime, x1 prime is x1 plus y1 d theta from this equation, and this y1 prime is y1 minus x1 d theta. Now, this x2 prime is x2 plus y2 d theta, and this y2 prime is y2 minus x2 d theta. Now we will expand it with the help of Taylor series, Taylor theorem. Now, since on the right hand side this potential energy is function of the unprimed quantity, so it's better if I write it as u x1 plus y1 d theta. So it is also a function of, I have to replace u prime to u because now it is a function of unprimed quantities. Y1 minus x1 d theta, this is x2 plus y2 d theta, this is y2 minus x2 d theta. Now I will expand this expression with the help of Taylor's theorem. So this will be u x1 y1 x2 y2 plus, this is y1 d theta curl u upon curl x1 minus x1 d theta curl u upon curl y1. From this it is y2 d theta curl u upon curl x2, this is minus x2 d theta curl u upon curl y2. You can go through the Taylor's theorem. For this, I had used the expression of Taylor's theorem and write this expression. So this is also discussed in the previous lectures, how we can expand the expression with the help of Taylor's theorem. Now we will rearrange this expression as u x1 y1 x2 y2 plus d theta is common, y1 curl u upon curl x1 minus x1 curl u upon curl y1 plus d theta again common, y2 curl u upon curl x2 minus x2 curl u upon curl y2. So I have rearranged the expression. Now the left hand side is u x1 y1 x2 y2. So from this expression we can write d theta y1 curl u upon curl x1 minus x1 curl u upon curl y1 plus d theta y2 curl u upon curl x2 minus x2 curl u upon curl y2 is equal to 0. Okay, so I have rewrite the expression as this. Now this can further be rearranged as y1 curl u upon curl x1 minus x1 curl u upon curl y1 plus y2 curl u upon curl x2 minus x2 curl u upon curl y2 is equal to 0. So expression is further rearranged. Now, as we discussed in our previous lecture, force is a negative gradient of some scalar function. So this is curl u upon curl x. So this can be replaced with the help of expression containing the term force. So this minus curl u upon curl x1. What is this curl u upon curl x1? This is the force Fx, x component 2 1. What is the meaning of this 2 1? The x component of force on particle 1 due to 2. Okay. So I will replace curl u upon curl x1 with the help of fx21 with the negative sign in this expression. Similarly, minus curl u upon curl y1, this gives the component of by force F on particle 1 due to 2. Similarly, minus curl u upon curl x2 is fx12 and minus curl u upon curl y is fx21. So I will rearrange the expression with the help of this fx f by component. So it will be minus y1, this curl u upon curl x1 is fx21 minus plus x1, this curl u upon curl y1 is fy21 plus this y2 curl u upon curl x2, this is x2, this is y2, is fx12 plus x2 f by, this is fy21 is equal to 0. So I had substituted the value of curl u upon curl x as negative fx. So because force is negative gradient of some scalar function, which is the potential energy. Now I will rearrange this expression as x1 fy21 minus y1 fx21 plus x2 fy21 minus y2 fx12 is equal to 0. So I had rearranged this expression like this. Now, what is this x1 fy minus y1 fx? This is the z component of torque on particle 1 due to 2. So I will write it as tau z 21 plus tau z 12 is equal to 0. How I write it is I will explain later. First we will rearrange this expression. So from here we can write it as tau z 21 equal to minus tau z 12. So it is Newton's third law as applied to rotational motion. Now if Lz1 and Lz2 are the component of angular momentum of particle 1 and 2 respectively, then this tau z can be written as d by dt Lz. Okay, so I will rewrite this expression as d by dt Lz. This is 2-1. 2-1 means force on, this is coming from fx21, this is force on particle 1 due to 2. So this is Lz1. What is the meaning of this Lz1? Angular momentum of particle 1, and z stands for its z component, plus d by dt Lz2, this is corresponding to second particle, is equal to 0. So I can further rearrange this expression by d by dt. This is Lz1 plus Lz2 is equal to 0. So this is 0 only if Lz1 plus Lz2 is equal to some constant quantity. So if this is constant only, in that case its derivative is 0. So what is this Lz1 plus Lz2? This is the angular momentum of the system, total angular momentum of the system along the z axis. So from here, if the frame of reference is rotated about the z axis through small angle d theta, the z component of angular momentum of the system remains constant or conserved. So this is the conservation of angular momentum or law of conservation of angular momentum. Hence, the law of conservation of angular momentum follows from the rotational invariance, that is isotropy of space. Now, I am explaining how I write this tau z 2-1. So, what is torque? Tau is R cross F. So, this tau is equal to, let R is x I cap plus y j cap plus z k cap, and this F force F is f x I cap plus f y j cap plus f z k cap. So I will substitute the value of this I cap, j cap, k cap. You know how to write the cross product. So R is x I cap by j cap plus z k cap, and this fx, fy, fz. Now this tau contains all the components along the x-axis, y-axis and z-axis. So along I cap it is y fz minus z fy, okay, from these two terms. Minus j cap it is x fz minus z fx plus k cap. I am solving this determinant term. K cap, this is x fy minus y fx. So this tau is tau x I cap plus tau y j cap plus tau z k cap. Now if I compare the components of I cap, j cap and k cap, then tau z equal to x fy minus y fx. So in this expression is x fy minus y fx. That means this is the z component of torque. So there is no term like this, there is no term like this. So I have not written any term like tau x or tau y. So there is only term containing x and fy. So this is coming from the here. So this is from tau equal to R cross F. You have learned in your +1 classes how to write the torque. So this is the z component of torque. So I write it tau z. Now there was 2-1. This 2-1 is coming from fx 2-1. This is coming from the force on particle 1 due to 2. So that's why I write tau z 2-1. Okay. In this term it's 1-2. It's 1-2. It is 1-2. So I write 1-2 here equal to 0. So this is all about the isotropy of space and how it leads to the law of conservation of angular momentum. Thank you for watching. If you have any doubt, you can write a comment or you can WhatsApp me on my number or you can write a mail to me. Thank you for watching.